Hi, I'm Sam Mumford, and I'm going to be talking about my work on adding face masks to faces using GANs. So the base problem is that facial recognition is used all over the world right now, but people have started wearing face masks due to the advent of COVID-19, and that makes facial recognition fail. So what I want to do is I want to make new data sets of people wearing face masks by adding face masks to faces using GANs. And there's a data set of face masks artificially superimposed on faces, which is my main data set that I'm using. So the first approach I used was using a stim GAN. What that basically does is it adds to the standard GAN loss function a term that penalizes making changes to the images. And I implemented this convolutionarily in both the generator and the discriminator. And the initial performance was quite poor. So this was with 4 ResNet blocks as the basis. And you can tell that it's finding the mouths and it's making them blue, but it's making a lot of unnecessary changes to the images, and it's not making realistic face masks. So I doubled the number of ResNet blocks up to 8, and now the performance is okay. So it's recognizably adding face masks to faces, but it's again still making unnecessary changes, especially in the corners of the pictures. So rather than just continuing to make this model larger and larger, I switched over to a cycle GAN. And so a cycle GAN, instead of just adding a penalty for making a change to the base image, defines a new pair of generator and discriminators, though the F generator. And so you'll first generate a picture of a face with a mask on it, and then you'll try and reproduce the original image. So you use the second generator to make a base face again. And then you penalize based on how dissimilar your prediction of the base face is from the actual base face. And so this is the best performing image-to-image translation GAN for most tasks, but it does require you to train a whole second set of models. So it's computationally expensive. And the benefit, though, is that even the first generations of the cycle GANs outperform the SYN GANs. And then with additional hyperparameter tuning, which you'll have to go to the base paper for, the performance became quite good. So the FID scores were less than 30, and the artificial masks that I'm adding on are virtually indistinguishable from the base data set of artificial mask pictures. So we then want to use these images for facial recognition problems. And what facial recognition basically comes down to is you're going to have an encoding of a face with a mask on it, and you're going to have a base encoding of a face. And I want the encodings of the faces with masks added to match the encodings of the base face according to cosine similarity. And I can use my GANs in 2 ways to accomplish this goal. The first one is by generating paired face and masked pictures. I can find what the encoding of the face mask feature vector is, and I can project away the encoding on that axis. So this is basically like the language debiasing model to strip the masks. And then the second way is to literally strip the mask using the generator that you get, quote unquote, for free as part of your cycle GAN model. So in English, for facial recognition, what I care about is that my face with a mask added to it is approximately my original face after appropriate processing, and that my face with a mask added to it is dissimilar to all the other faces after appropriate processing. Which means that I want my second column here to be large and my third column here to be small. And without doing anything to strip off my masks, I find that the original faces and the face with the mask on it are too dissimilar to be useful. But with both my projection methods, I improved the distinction between my face plus mask and original face and other faces. And actually with the cycle GAN stripping model, you can get up to above 3 standard deviations of separation and an error rate of 0.2%. So thank you for your time and attention and for a great quarter.